we go.
I love to hear my laughing.
I'm always edit out your laughing. Okay.
Why do you be interested?
So, all right, so polar covalent is kind of in between covalent and ionic. So you think of covalent, a covalent bond is where two atoms each put in an electron and they share them, and that electron, those two electrons hold those atoms together. Ionic is where one atom takes an electron from the other one, and then they're attracted because they have opposite charges. So you have an in-between category where the electrons are kind of a little bit closer to one than the other, but not quite so much that we would call it ionic. So let me kind of draw this out for you. You see what I mean? First, let's do covalent bonds. All right, so let's imagine, we need to write this. Let's say carbon and hydrogen are going to bond, okay? We got one hydrogen over here. Let's do a little X. And one carbon over here. I'm putting them far apart on purpose. Okay? So there we go. And these two are going to react and they're going to bond together. And let's imagine that this dotted line represents the halfway point between the two, the exact middle point. So when these two react, because they're going to form a covalent bond, this electron and this electron are going to both go in the middle, sort of. You're going to have your two electrons almost exactly in between these two. Not quite, because they're not the same atom, but pretty close. So those two electrons are right in the middle. And now both of these atoms are attracted to those electrons, and that holds them together. So that's your covalent bond. Now I'm going to leave a little space here. I'm going to do ionic bonds. So let's pick something that will be ionic. Let's do potassium and fluorine. So potassium, let's do an X for this one. And fluorine, good, 7 electrons. Okay, so these two are going to react, and let's do a little dotted line. And imagine that's the halfway point. So for these, what's going to happen is this electron is just going to go over here, and fluorine's going to keep this one too. Now we'll have both of them closer to the fluorine. I'll make these big just so you can see. So those are the two there. The one was from fluorine, the other one's from potassium. They both come over here to the fluorine, and so now this has a minus charge, this has a plus charge, and these two are bonded together because they have opposite charges. So covalent, they share the electrons. Ionic, one takes the electrons from the other. But what if the electrons were not in the middle, but they weren't quite around one atom? They were kind of like closer to one a little bit, but not too close. So let's imagine that. So this is going to be called polar covalent. So let's do hydrogen and oxygen to make a polar covalent bond. Here's your hydrogen. Here's your oxygen. And we'll imagine the midpoint between these two. So what's going to happen is these two electrons are going to go into the middle, but they're not going to be right at the middle. Right? We'll leave our dotted line. They're going to be like over here. Right? So they're almost exactly between them, but a little bit closer to the oxygen and a little bit farther from the hydrogen. This is a polar covalent bond. And what happens with this is because these electrons are a little bit closer to the oxygen's a little bit negative, but not -1. It's a tiny charge, like -0.1 or 0.01 or something. It's a very, very small charge. And this hydrogen's a little bit positive, like +0.1 or 0.01, some very small number. So for that reason, the water molecule, which looks like this, there's your oxygen, there's your hydrogen, the water molecule is polarized. Polarized just means there's poles. There's a plus and a minus, or a north and a south, or whatever you want to call it. So the oxygen is going to be a little bit negative. Not a whole -1 charge, just a small, small minus charge. And the hydrogen ends, this side, is going to be a little bit positive, +0.1 or +0.0, some tiny number like that. So for this reason, there is some small attraction between the hydrogen on this molecule and the oxygen on this molecule. Not as strong as this attraction. This covalent bond here is very, very strong. There's some small attraction between the molecules. And that small attraction is why water is a liquid instead of a gas. If there was no attraction, these just fly apart and be a gas. But because there's some small attraction, it keeps them liquid and pulls them together a little bit. So that's what polar covalent bonds do. Now, I told you how to know if something's a metal or ionic or covalent, right? I said ionic is a metal and non-metal together. Covalent's two nonmetals. But then we got to have this in-between category, so how do we figure that out? And so that's what I'm going to give you now. And we're going to use electronegativities to figure that out. And for that, I'm going to do PowerPoint. And now I need somebody to just push stop on the video.
Okay, so everything that I explained during the lecture, the beginning part of the lecture, is basically written here. If you're one of my students, you should copy down what it says here in the PowerPoint. Also remember, any PowerPoint that I have, I always put a copy of the PowerPoint itself, a link to it, in the comments section. So if you, in this video, you go down the comments section, you may have to click on Show More. You'll see a link to the PowerPoint and to the worksheet for this lesson. So copy this whole thing. I'll just briefly go over this again and then I'm going to move on, but you might want to stop the video to give you time to copy these notes down. So polar covalent compounds are sort of an in-between type of thing, where you have, with a covalent compound, you have covalent bonds in which electrons are shared equally between atoms. In an ionic compound, you have ionic bonds in which one atom takes an electron, or more than one sometimes, from another atom. In a polar covalent bond, you have something in between where the electrons are shared, but they're a little bit closer to one atom than the other, and so the one they're closer to tends to have a negative charge, and the one they're farther from tends to have a positive charge. Because of this, the molecules have some small attraction for each other. And so here we look at water molecules, and we see that the hydrogens are attracted to the oxygens and vice versa. So we have this weak attraction between a hydrogen on one molecule and an oxygen on another water molecule. This is nowhere near as strong as the attraction between this hydrogen and the oxygen in the same molecule. That's a covalent bond that's very strong. The attraction between the hydrogen on this molecule and the oxygen of a different molecule is very, very weak. So we need to be able to determine if things are ionic, covalent, or polar covalent. And remember, I had already given my classes this simple rule that if we have a metal and a nonmetal, it's ionic, and if we have two nonmetals, it's covalent. But then what about the polar covalent? And so here we have to use electronegativity to get a better answer. And so electronegativity is simply a measure of an atom's pull on electrons. So some atoms have a very strong pull, and they hold on to their own electrons very well, and at the same time they have a pull on other electrons and take electrons from other atoms. On the other hand, metals have the opposite. Metals have a very weak pull on their own electrons, and they not only don't usually take electrons from other atoms, but they tend to lose their own valence electrons, and they give them up very easily to nonmetals. This is a periodic table of electronegativities. There's a copy of this on the last page of the worksheet, and you could also simply Google periodic table of electronegativities. Sometimes they vary slightly in number, but basically you get the same answer. One notices that fluorine has the very highest electronegativity, meaning that fluorine will take electrons from any other element, or in some rare cases with some of the other ones with very high electronegativities, it could form covalent bonds, but it has the strongest pull, and so there are no elements that are going to pull electrons away from the fluorines. On the other hand, we have francium on the bottom left, and that's the pattern. It goes from top right to bottom left. So as it goes from top right to bottom left, the numbers get lower. And so francium has the weakest pull on any electrons. And so it tends to lose its electrons no matter what it's around. Any other atom can come by and take electrons from francium. And so that's what we see. So you'll notice the higher numbers with all the nonmetals, and they always tend to take electrons from the metals. And then we have ionic bonds. And then you'll notice that the nonmetals themselves are pretty similar, so when they bond with each other, we often have covalent or sometimes polar covalent bonds. And so how much of a difference is enough to where we have something's either polar or ionic? And so here you take a look and make sure you copy down the last slide. Not the last one, the one before that. And you want to copy this table down also. So here's the rules. And they vary a little bit from one table to the next. Not all books agree. But generally it's agreed upon that anything from 0 to about 0.4 is going to be covalent. So what that means is if I have a compound and it has two elements and the difference in their electronegativities, like if you subtract one from the other, is small, if it's less than 0.4, then that bond is going to be covalent. So what I'm really saying here is if the electronegativities are close to the same, then we're going to end up with a covalent bond. Now, on the other hand, if they're really, really far apart, like fluorine and sodium, for example, fluorine's 4, sodium's 0.9, the difference is going to be really big. That's going to be, what's that, 3.1 difference. That's way over the 1.7 mark here, so that's definitely ionic. And I'll give some examples in a minute, but this table tells you how much of a difference you need for it to be covalent, polar covalent, or ionic. So here's an example, actually. Sodium chloride. So you know it's made of sodium and chlorine. And if you want to take a look and figure out if this is going to be ionic, covalent, or polar, you go back to your periodic table of electronegativities, and you look up here at chlorine, and it's 3.1. And then you come over here to sodium, and it's 0.9, and you subtract. And you always do the biggest number minus the smaller number. And so 3.1 minus 0.9 gives us 2.2. Right there, 2.2. And 2.2 means it's ionic, because according to our table, anything greater than 1.7 is ionic. Here's another example. We're going to look at water. And I want you to notice that this 2 doesn't matter, because all we're talking about here is the bond between one oxygen and one hydrogen. Any hydrogen, doesn't matter which one on the water molecule, because they're both going to be the same. They're both bonded to the oxygen. So the bond between one oxygen and one hydrogen. So we go back to our periodic table. Oxygen is 3.4, you can see, and hydrogen is 2.2. So you just subtract those two numbers. 3.4 minus 2.2 is going to give you 1.2. 1.2, well, that's in the middle here. That's between 0.4 and 1.7. So that's going to be polar covalent. Let me give an example of a covalent one. Fluorine gas is actually made up of pairs of fluorine atoms stuck together. They're very unstable by themselves, but two of them can stick together and be a little bit more stable because they fill each other's outer shell. And the bond between them, since they're both the same atom, you just subtract the same number from itself, 4.0 minus 4.0. So the difference is going to be 0. And clearly, anytime the difference is 0, right, you're going to end up with a covalent bond. Anything 0 to 0.4 is covalent. So anytime you have the same two atoms bonded to themselves, so two fluorine atoms stuck together, or two oxygen atoms, or two chlorine or bromine atoms, then you're going to end up with a covalent bond. Methane is another one that's covalent, and that's it. So you get the idea. All you have to do is look at the two elements in the compound, you subtract their electronegativities, and then if the number falls between 0 and 0.4, it's covalent, 0.4 to 1.7, it's polar, and 1.7 or greater, it's ionic. And my students should copy down the title and this too along with the table just so you remember. That's it. And again, like I said, the PowerPoint and the worksheet are both going to be in the comments section. You have links to both of them.